Yeah, okay, you will do. Yeah, I'm only sharing your slides.
All right. All right, everyone. So I'll talk about general miscellaneous recipes for full stack robot learning. Okay, so to start with a high level, low level, and basically kind of all the recipes that you need to scale robotics today. So what is the point of using learning in robotics? There's only one goal: to have robots generalize. Okay, which means training them for several tasks in several scenarios. So if you are doing one task in multiple scenarios or many tasks in one scenario, you don't really need learning. You can automate them by other ways. But machine learning goal really is to drive generalization across tasks, across scenarios. So, what is the major recipe that we have seen in the last 4 or 5 years in AI? Right, the main recipe has been big data sets, big models equals to magic. Pretty much the same recipe across language, across vision, across all the areas. There is innovation happening. People improve architectures, they improve this and that, but largely at high level, you have big data, big models, and your end application. Right now, field after field, this recipe is applied to different scenarios. First was language, speech, now vision, and you can see the gap widens between academia and industry as this recipe works. But the story is a bit different in robotics. It is considered the next frontier for AI models. Okay, because in robotics there is no data. Unlike language or vision, even the first step we have of big data is missing in robotics altogether. I cannot train big models because there's no big data, so I can't really do anything about it. In fact, I call this the chicken and egg problem of robotics. To get data for robotics, we need robots to be deployed, but to deploy them, they need to work, but to work, they need data. So what comes first? Do deployments come first? Data comes first. It's an open problem in robotics. And which is why you see all these demos around the world where for the last 30, 40, 70 years in robotics, there have been demos, lots of demos. But still, these robots don't really work well when you deploy them out there in practice. Even in the simplest of cases, they fail to complete the task. And you can collect data on the hardware, but it's super expensive to scale data on the hardware, especially at the level of GPT models that we have in VLM land. Okay. So one research direction that's really taking attention these days is using LLM or VLM models for robotics. Like initially, people did LLM for language. They combined LLMs with video models or vision models. They have VLMs. Now the next direction is robotics. So what people typically do, they take pre-trained language models or vision language models and they fine-tune with a small amount of robot data, and they start calling it robotics foundation model, which is a new term everybody uses these days, right? And we may be partly responsible for this because I had a paper 3 years ago. It was the first paper showing language models for robotics. But this paper was a satire, and I'll explain how. And what we showed here is you can use language models to generate plans for any robotics task. So what we did in the left side, we prompt of high-level task, step by step what to do, and then ask for new task, what should the step be? And then we map these steps to actions on the robots have. And if you recall, there are many benchmarks in vision community for robotics, virtual home, AI to thought, and all those, etc. And in all those benchmarks, the actions are language. And these benchmarks are sold as the action is abstracted to language because the focus is super long term. The tasks are browse internet. The robot has to get up, or the human has to get up and move to a different room, find the computer, sit down on the computer, then open the internet and do all this. But turns out when you abstract the language or abstract the actions to language at such high level, you can completely solve these benchmarks using no data from the benchmark itself, just from off-the-shelf LLMs. So this paper we published at ICML 3 years ago at this point, or slightly 4 years ago. And this paper was a satire on the benchmarks, that this is not robotics. Like this is a language problem. And the goal was to show navigation in simulation with highly abstracted scenarios is a language problem. It's not a robotics problem. But the satire got completely missed. And in fact, this became a popular area of research now called language for robotics. And there are tons of papers. This is if you go to a robotics conference today, most number of papers are in this VLA land, where do people do the same thing, but now instead of simulation, they are doing real, and the actions are still abstracted to language level at the very end. Okay. Now, these models largely still have 99% data from language or vision and a small amount of data on the robot, and they fine-tune the system with the tally of data, right? So when you see all these demos, it's a Gemini robotics demo or anything, you will see that they are largely about talking. Hey, robot, can you put, I'm tired today, can you give me something to eat? And robot picks up some bar, which is right there in the front, and picks up and gives it to you. Or put this pink ball in blue box, red apple in green box, and very simple pick and place examples. Most of the demos about language, and the reason is because they are trained only on language data. So the generalization of the robotics part is still very, very limited. And that confuses people who are not roboticists to thinking this is a robotics advancement. But talking to a system already exists on your phone. You don't need robot for that. You can respond, etc. The robotics hardness comes in the task they are doing. So if I focus on the tasks that these robots do, like simple pick and place, for example from Gemini, and I can show you results from 10 years ago, 8 years ago, that can do much more complicated stuff without having access to large-scale GPUs or large-scale compute or data. This is paper from Berkeley 8 years ago called DexNet from Ken Goldberg's group, done by one student on probably one GPU machine, not large data, but they can already do all the complex tasks that you see in today's VLA models and all these fancy scenarios. And again, no large-scale learning, very simple. Then what's the catch? If you think this is very recent, I can go all the way back to this video.
One exhibit at the Nuclear Congress in Philadelphia has the perfect formula for popular appeal. Two amazing hands plus
so what you are
pretty
seeing
girl.
here is
The purpose of
a person is controlling two robot arms.
precision of the
The
master's
person at the back,
used
lighting a matchstick, very complicated
But
task.
incidentally, it shows the boss how his
Lighting a
secretary can light a
cigarette,
cigarette
also
and keep
puts a
right on
lipstick on
working.
her, and gets the ear of this result.
The skilled operator of the
Guess
electronic
from the
device
audio
now
and
sets
the
himself
video.
a more delicate
How old
and
is this?
delectable problem. And the hand goes to it with a marvelous dexterity.
50s, 60s, you get it right. What I should have done is I should have made this color and changed the audio to more modern times, so you could not guess. Like if you look at today's paper in robotics, this is a system, like I showed, this is Google system, right? This image, 2-arm system at the bottom, it's controlled by 2 other arms. This system has been existing from 1957, 68 years ago, way before personal computers, way before computer vision even became a field. Robotics already was this good or this bad. It has been the same almost the last 70 years. So what is the big mystery of robotics? Why does it not work? In fact, ignore this, even like the first computer vision thesis from MIT was actually not on computer vision. It was on robotics. And this was the end result of the thesis 60 years ago, this copy demo, where the robot sees the photo in the front and then arranges the block to make the photo, right? Now you may be seeing all these humanoid demos on Twitter, LinkedIn, humanoids doing parkour, jumping back and flip, and people are like, okay, robotics is coming to kill us all or something. Look at this is a demo from 30 years ago. These are all humanoids doing much more harder tasks than people do today. Playing foosball with a person, on the left doing juggling. And you will see the leftmost one also balances a stick in the hand. Super complicated. If somebody writes a paper like this today with Sim to Real, they will get a best paper award in robotics conference this year, for sure. So what is the catch here? Well, why are there no still robots around us if robotics has been going for so much longer than anything else? And the reason is because in robotics, the hard part is not language, it's robotics itself. The hard part is the skills, the motor movements, and very hard to generalize them across scenarios, across tasks. All these demos that you saw, same as demos and videos today, they're very hard to transfer if you change the object, if you change the surroundings, if motors heat up, or if robot changes, everything has to be redone and recustomized, which is why robotics has not been around. And so this was the learning from, so robotics is one of the oldest fields, it's older than vision. And this was the learning from the first 30 years of robotics. It's called Moravec's paradox. You might have heard of this, but hopefully I'm making you feel it. 57, 67, 87, 97, then people realize, wait, robotics is not easy. In fact, what they thought was hard turned out to be easy, like reasoning, language, playing chess, etc. This was very easy. But moving actually the body to do anything reasonable in the real world turned out to be very hard. And which is why we don't have robots today. This is one of the classic examples you might have seen where you can beat chess players 30 years ago, but we can still not have a robot to move chess pieces on the board manually. So how do we go about solving this problem of robotics? Okay. Well, what has changed between now and the earlier time is today we know some recipe in AI that works. The recipe is big data, big models. Okay. Now we can have big models in robotics, but we don't have is big data. So how do we solve it? Well, we cannot hope to collect data on the real robot forever. It will take too long. What we can do is we can look for alternate sources of data. And this is what we have been working on in our group. It's a very open problem, but there are two sources, I believe, which can be used very heavily in robotics, and they are very big sources. One is simulation. The other is human videos. Okay. Now, this hopefully now may make sense. Why do people use simulation in robotics so much? And this next push, I think, will be human videos. Both of these are super scalable. You can collect trillions of samples for videos that are already out there on the internet, right? So very scalable. Let's talk about simulation first. So I've been working in simulation for a very long time. I'll not go into the details of how things work. Like we released the first paper from our group on Sim2Real about 4 years ago. It was then 5 years ago. So 5 years is a long time in machine learning and robotics field. This was the first paper, and at that time, now probably you see all these results off the shelf in companies. The idea was very straightforward, but still the same idea in all papers, all results today, in all humanoid to quadruped, all results, even after 5 years, because the idea works. The idea is very simple. Phase 1, reinforcement learning. Phase 2, supervised learning. You train via large-scale reinforcement learning in simulation with privileged data. Data could be your body sensing, physics, randomization, etc. Phase 2, you distill all that expertise into a model with input that is available on the robot, like camera image or something. And you can train both the phases in simulation. Okay. In short, teacher is student, teacher is RL, student is supervised learning. This is the exact same recipe across all Sim2Real papers today. Any result you pick, maybe slight modification, like to publish a paper, to have some innovation to publish the paper. So have some loss over here, some loss over there, but largely the same idea everywhere. Okay. And this works really well. This was 5 years ago. I don't know if there's sound. Can you increase the sound on the screen?
Oh, yeah.
No, the sound is full here. So here, and you can see it works really well. I mean, this is much harder problem. Here you are taking the robot is training for vision. Again, not now. This is 3-4 years ago. So you can do very well. And it's all end-to-end learning, no magic, no 3D, no abstraction, no explicit perception. You just take camera images input, you output command to motors, you train on Sim2Real with large-scale data. No abstraction, nothing. Kind of against what CVPR stands for. But it's okay, I'll show the importance after. So here you can see stairs. This robot doing stairs is not like humans doing stairs. It's like humans doing walks, because the height of stair is same as the robot. Again, 4 or 5 years ago. Then you apply this to all these papers won awards at the time because it was very new work, the simulation. Now it's very popular. Here you put the arm on top. We just tape the arm. You can see the blue tape on the robot. It's not even fixed properly. And the arm and body can react together. It's called the area of whole body control. It used to be a separate area where people did upper body, lower body separately. Now it's all end-to-end single model. Now what I'm presenting here is the magic of end-to-end. Like if you have data and the right kind of training, it really works. There is no issue in that. Even like something like Pathak. Here this robot is operating from just the front camera. No other sensor. Very low cost robot. Couple of $1,000. Again, this is 3-year-old. So you can see all these systems work really well without doing anything fancy. And they work in lab, they work outside lab, no magic. Literally, I've been presenting this for 5 years. asking people to use simulation, and now they finally use it, but for the wrong application. I'll show in a bit why. Okay, you can apply for humanoids, whatever. It's trying to show robustness to the oil, this oil being the sheet. You can apply it to manipulation, but more custom manipulation and all that. The story really works. I can apply it to all these scenarios. And the thing is, if you are getting started in simulation today for these tasks, it's already too late. It's 5 years too late. Okay. So the question, and we have been giving demos, by the way. This is CVPR, I think 2 or 3 years ago. We did live demos of over there, and this paper was submitted the day before CVPR to Coral. So when it works, it really works. You can submit the paper, and next year giving demos in front of thousands of people everywhere. Again, Coral, New Zealand, it really works. The question is, what's next in Centauri? Unfortunately, simulation has been working well for a while, but now it's super popular for robotics. And almost all major results today, they're all from simulation, like all these humanoids, all these other things. So what's next? And here I would say locomotion or mobility problem is almost solved. Almost solved and definitely solved by academic perspective. Like there's no need to tune losses, etc. It really works at scale. You can really get the systems work across scenarios. What is the next frontier is manipulation. Okay. Now, manipulation is much harder because one hand has as many degrees of freedom as the whole body. Like if you take a robotics hand, it has like 16 DOF, 20 DOF, and one hand and full humanoid has 20 DOF, 20 degrees of freedom. So a hand is as complex as the whole body. So the amount of things you can do in manipulation is huge. And turns out even the scale of simulation is not enough to train these systems in an end-to-end manner. And that's where I want to go into a case study of manipulation for Centurion. Now, the magic behind all these results, all the videos I showed, is the phase one, large scale RL in the teacher network. It's all happening in simulation. Okay. When I say large scale, it's really a large scale. It's 100 billion plus samples to get those results I showed right now. Okay. What is the main result? What is the most popular RL method that people use today? Anybody? PPO? Okay, right? PPO. If you have not heard the term PPO, go ahead and look it up. It's the magic behind everything. Every major result in AI, from DeepMind, OpenAI, everything is driven by PPO at the back. When I say PPO, I mean variants of PPO, but largely PPO, right? PPO, GRPO, they're all the same, pretty much. So like AlphaGo, AlphaZero, Dota, like Kipling, StarCraft, those kind of results. Even GPT models like ChatGPT was PPO, O3, O1 reasoning models PPO, DeepSeek R1 PPO. All these models are using PPO. In robotics, all the results I showed right now, they're all PPO. All of humanoid demos that you see, they're all the same method. They're all using PPO by extension. Right? Now, PPO has become kind of SGD or Adam in RL. So what usually happens is when you're training networks, how often do you tune Adam anymore? Nobody tunes Adam, nobody tunes SGD. It has become so fundamental truth. It's buried inside your stack, and you never look it up, and then you never improve it. You tune architectures, you tune data, losses, but not the optimization, which is fine for language or vision because these are very mature fields. People have already trained models at billion, trillion scale, which work very well, but not for robotics. The reason this talk is called full stack because in robotics, everything is broken. Every part has to be restudied and reanalyzed. So now PPO, the way it works, so what is RL? RL is a method of hit and trial. You might have heard. What is hit and trial? You have to try billions of times, see which trials are good, and then use those trials to distill the policy back and then find the right answer, right? So hit and trial, so which means you have to try multiple times. And people use PPO. How does PPO work? I mean, one example here is used on simulation, etc. One cool fact is, if you look at the RL in the last 10 years, the number of data that is being used in these RL methods is growing exponentially. This is log in the linear and the log scale. So it's growing exponentially in the last 10 years. And now we can also have simulations which are on GPU. So you can really run them fast enough to have lots of billions of trillions of samples very quickly. But the issue is, which nobody notices, underlying the SGD of RL is broken, which is PPO is broken. So what happens here, as you increase data, as you increase batch size, after a certain point, the PPO itself stops working. as in stops improving. Okay, let's take a step back. Why am I showing this? For manipulation, the task is more complex. The more complex the task is, the bigger your search should be. The bigger your search should be, which means the more examples you should try in a single batch. Your batch sizes have to be really, really big. PPO required 16,000 examples underneath. You can scale it to 100,000 and more for locomotion. But for manipulation, for doing anything complex, you need a much bigger search space, much bigger batch size, which means you will put more resources, more GPU as natural. And turns out you can do that, but the algorithm can only improve until certain batch size. So in the curve, it is showing that beyond 25K or 50K, the performance of the algorithm stops improving, the blue line. But the actual performance is a red line on top, which you can go much higher. But even though you're putting more money, more resources, it's not improving. Okay, and that is the fundamental flaw of reinforcement learning, which people used to know this when it came in the beginning in 90s, but then people forgot about it completely because it began working. But now, so earlier it used to be small scale, people knew about the issue, but at big scale, it began working very well, like billion samples, 100 million samples I showed earlier. But now when you go to much higher sample size, it again does not work. And the reason is as follows. Because what you are trying to do, you try more and more examples. So how does RL work typically? It works as follows, very high level view of RL. You have a policy you're training on the fly. You try it on a lot of examples in the first trial. Okay. From those examples, you figure out which of those examples have high reward or are good examples. Then you take those examples back, you incorporate them in your model or policy, and then you again roll out the policy to get more examples, and then you again pick the right examples, you discard them, you again. That's how you repeat. It's called on-policy learning. The policy you are learning is used to collect more examples to train. Okay? So now the idea is, as I said, for manipulation, you need way more complex scenarios, way more complex. So you should be trying a lot more in parallel. But then there is an issue comes. The issue is deep networks, they tend to converge to certain behavior. Even if you resample or sample them, they will generate some behavior which you have seen as positive so far. So what happens even as you increase batch size in these models, as you increase batch size, as you are sampling from the model, whether you use 10 GPUs or 1,000 GPUs, whether you use a batch size of 1,000 or 100,000, they look very similar. You are largely sampling in a similar region. So the underlying optimization cannot take benefit of the compute you have. So the scaling law doesn't apply here. It's actually saturating. So as you scale, no matter how much money you have, you cannot get higher performance because it's broken fundamentally. The model you are training cannot behave in a diverse way because it will. Does it make sense? So how do we fix this problem? Now there are many fixes possible, and I'll show one paper we presented at ICML this year. It's called SAPG. It tries to address this issue, but there are multiple ways you can resolve it. But it's not easy to resolve. It's a fundamental issue in RL internally. Okay. So what we say is, okay, you want to get a model which can learn with a lot of data. So your goal is to use more data to train these models. Okay. But data is not diverse. So solution is ensembling. You can make it an ensemble to get data. But the catch here is it's not like the same ensemble we use in computer vision. In computer vision, we use ensembling for inference at test time to improve the accuracy. But in robotics, you don't have time for ensembling because you have to operate and output action in milliseconds. If a robot is falling, it has no time. It has to operate at a very, very high frequency, millisecond level. So it has to be a single model for deployment. Make sense? But for collecting data, I can use ensembling. But then the issue is the math breaks because I cannot, the data that is coming from ensemble is not my main model's data. So I cannot use the data directly. It's not on policy. So this is the main flaw in RL. It has been for forever. So what we do is we do a simple fix to it with some approximate math. So the idea is we create K policies, okay, multiple children policy and one leader policy. So pi 1 is leader, 2, 3, 4, 5, 6, but they are all children policies. If I have million examples or 10 million compute, I divide that into 10 policies. Okay. As I increase my compute budget, instead of training one policy, I will train K policies. Now, per policy budget is still very limited. Does it make sense? Okay. But I still need to train I still need to train the main policy to get all the experience from other children policies. So now I will increase my batch size, but if I increasing batch size, I'll create more networks. I'll use them to collect more data, but I still want to assimilate the data of all the other networks into the same policy. So which is why it's called split and aggregate. So here we modify the PPO objective. So this is the objective. Now you want to use data from other policies, other networks. What's the trick in mathematics for that? Importance sampling. So you can importance sampling, you can incorporate data from other policies back into this. Now the math breaks here because it's a multi-step process, intractable. You make some approximations to make it work. You find the answer, whatever we deploy, etc. Okay, high level idea, how it works. You have a lot of environments, but instead of training a single model from everything, you train n models, you split them into multiple models. Now, when you split them, they're all different networks, so they won't collapse with the same behavior. So your data will remain diverse in these scenarios. But then what you do, you combine the data from all the children policy back into the leader policy. So in the end, you are training a single policy, which is the pi1 at the top, but you first split that, you get diverse data, then you combine it back into the same policy, and you do some tricks to make the math work, so that it's all consistent. Okay. So this is called SAPG, and also this you can implement this very efficiently. So it's only 9% slower, but it works in complex cases. And we do have tricks to make it fast, etc. So it's a drop-in replacement pretty much. So here, what you see, some examples. So I showed sim2real works. So I show these results only in simulation, but for complex scenarios. It's a 7-DoF arm, and the hand is 16-DoF. So it's how much? 23 degrees of freedom. That's as many robots in a humanoid. So as many motors in a humanoid. So the complexity of this robot is same as the full humanoid. And the goal here is to move the object from here to here. And you can see it works well. And you can discover the whole behavior. And this is continuous control. So you are outputting 50 to 100 actions per second. You can change the task. This one is very complex. So here now we have two robots. Your goal location. So the goal location can come either to the left robot or the right robot. Okay. So this is equivalent to the state space of two humanoid size. So the robot is turning one cube, but whenever the goal comes to the next robot, it throws the cube back to that robot. It has to catch it, then again turn it in all directions. It's a very complicated behavior, and it's all emerging end to end. Now, for this kind of behavior to emerge, you have to really sample at a very, very large batch sizes. Otherwise, it doesn't work. So you can do any kind of task, etc. Now, here I will show you a plot. Now, plot is frowned upon in vision conferences, but here it's very important to show because this is optimization we're talking about. Ignore the bottom two plots. That's in standard environments. Top two. The pink line you see at the bottom is PPO. Now, imagine as a student, you're training these models. You will try billion reward functions, all combinations. You will try day and night. You will add priors. You will add data. You will add money. You will add compute. It does not work. It does not even rise to any value. While the blue curve is this model which works pretty well, but the underlying optimization is broken. Which is what I mean by full stack in robot learning. Because unlike language, etc., where you don't have to look for SGD or Adam, in robotics, every piece of stack needs to be studied. And here PPO is really broken because nobody has pushed PPO to its limit even today after it's being used worldwide across all the scenarios. Because even in language, GPT land, the batch size is nothing compared to robotics. What I'm showing for these examples. Okay, you can apply to more scenarios, real robot, etc. But you get the point. The idea is if you get the behavior, you can transfer it over time to robots as well. So I'll skip this part. Okay, now there is still a catch though. The catch is this approach works very well. It's all end-to-end, all training simulation, using nothing, no stage-wise processing, no abstractions. But there is a role for abstraction. It's not that abstraction should not be used, like priors. So there's a paper we had about 7 to 8 years ago in my PhD. It was a paper at ICML with no equations. So it is a miracle. It was a long oral talk at ICML. I really like this paper. It's a study, it's a psychology study. So what we do here, we create this game and we ask humans to play this game. Okay. Now, as a human, you know already what all you can do. There's a pink monster over here. That probably is a bad guy. I should not touch that. There's a stair over there. You can climb up. Those spikes are bad. But what if I showed you this? And I said play. And that's exactly what we did. We asked all the MTech workers to play this game with this information. It's completely random. Now you would say it doesn't make sense. Like, this is garbage, you're wasting my time. And that's what everybody told us. They wrote abusive emails to us, like really abusing us, that we are wasting, and people pay them extra money to having wasted their time. But the idea is, this is what RL is doing. When you train RL from scratch in these systems, this is what exactly it does. It has no prior, no idea. It has to try every single thing to figure out what's empty space, what's not. And when people say humans are more efficient than RF, it's total BS. They're not. They are efficient with priors. But if you remove the priors, like here, I remove the priors and left, they become very efficient. By just hiding one thing, this is real human trajectories from MTech workers. It becomes really worse. And for that game, it just looks totally random. So we don't even show it. It doesn't even make sense. So this is where we need to get priors, and this is where the vision part can really be helpful. Vision is not helpful to create stage-wise processing, but it's helpful to create abstractions which you can use for robotics. And this is where we use human videos to get abstractions. There are many ways to use human videos. I don't mean here imitation learning, not by using robot data. I mean more by using human data. You can see humans do things and copy it. So one idea I mentioned here is like affordances. Okay, affordances has been an age-old topic in computer vision, like 40, 50-year-old. But the thing is, no two computer vision papers have the same definition of affordance. Everybody defines it as they wish to, as they can get data, right? So in this paper, we actually transfer affordances to robotics, but we extract the affordances from data. Now the approach here is very, very simple, but just an idea as to how vision can be used explicitly for robotics. We take human video clips, we detect human wrist, we say wherever the human wrist in the scene is, and that tells us which object are humans interacting. Then we track the motion of human wrist over frames, and that tells us how that object should be moved. We can use this data to train an affordance model, which now you can use for robotics for many applications. Like this is a prediction of the affordance model. So these are all the predictions. These are all unseen objects. Even before I test my robot on this, I already know from human videos that humans generally touch the garbage bin on top, they touch the pan handle on top, or a knife over there, or the cabinet at the handle. And videos also tell you how do they move this. So now I can use these affordances as an action space, and I can already save a lot of computation and time to create these results. So here we create a world model, we train joint world model across videos and robot videos with affordances, but you get the idea. And you can transfer this across robots with a small amount of robot data and lots of human data. Okay. So here, what is happening is same model is being used across tasks, across scenarios, and this is all pre-trained with human video data where the action is. Now, human videos only have frames, ST plus 1, they don't have action. So affordance can act as a pseudo action for human videos, and that's how you use it for pre-training these models. And you can also incorporate practice at test time, etc. I'm going a bit faster, I think more time here. But you can see here, the more you pre-train, the more it helps. So only look at the blue line and the green line. And pre-training the model with human videos provides a huge benefit in terms of performance and transferability in all these tasks, right? And then now there are three ways. So one is using simulation, one is using human videos, which we use in all these scenarios. We use videos from YouTube. We align human hand with robotic hand, etc. But then the third data source today people use is teleop. Teleop is where you use data on the robot itself. Now this data is very high quality because you have to move the robot manually to control data. This is the equivalence of supervised learning in computer vision. Teleop is equivalent to ImageNet training. You collect the ground truth examples. They're very high quality. It takes 10 minutes to get one example. So it's super slow. Even if you hire a billion people on Earth for a century, you will not reach the same scale as GPT. So it's high quality, but very, very low. While videos are very diverse, but they're low quality data because they are not exactly robot data. So we have been thinking about how to combine these two things both. So can we use humans to collect robot data without carrying robot around ourselves? So these are some teleop examples. So teleop does give you very high quality tasks, very complex robots in the real world very quickly. Like this result took us a couple of weeks compared to simulation result, which took us almost 3 years for simple tasks. But the issue here is they don't transfer very well because they are trained with less data. So we created this new mechanism to collect data called DexY. I'm just showing this. Instead of carrying robots everywhere out of lab, what we do is we create a custom rig for humans to collect data. So there's a simple glove camera system. You can use this to go around and humans can just collect data. But this data is very close to robot data because you are actually transferring every coordinate of what humans does to a robotic system. Now, I believe this is a hack, this is a band-aid in the meantime. Computer vision has gotten really good that I don't need to use gloves, etc. I can use directly hands and I can probably transfer it with 3D computer vision as well. So we shouldn't be using this hand, but right now we are just for accuracy. So one person can collect a big data set from this approach without having access to big labs. Like today, Google, like the RTX paper in Google, we spent 2 years, hundreds of contractors. We could collect only 900,000 examples only in Google's kitchen. And here, one student in a week can collect a big data set very, very quickly because it does not require humans. It only requires you to go there to different scenes, collect data, and then move forward. The same approach how people collected SSV2 data set. But now this data set has real robotics examples. So we take it everywhere, and it works very well. We can combine this data source with other data sources. And since you're getting diverse data, it really works across scenes. Now the talk is titled recipes. So all of these are recipes and they have to be combined at some point into something. Currently, our combination is very boring. It's all code training. We get data from videos, data from the system, some robot data, and we just combine it together and train it all together. Now we have not really figured out how to put everything together yet, but this is how we believe it should be done. Like a lot of data from human videos, gloves, small amount of robot data, put all together into a single system in these environments. So here we are doing some simple tasks, but in diverse scenarios. You can do cloth folding. You can put all these things in the like flower pot. You can do pouring, spraying, in all these scenarios. Since you're not really doing data collection of the robot, you can transfer to any new robot also, any different arm, different hands, etc. And everything here is built in-house, except for robotic arm. Even these hands are built in-house. It's called Leap Hand. You can build this for $1,000. We have open source this whole setup. Very easy to build. And hands used to be $100,000 earlier. So it's a very huge reduction in price, 100 times. So just to summarize, so as I argued in the talk, the main problem in robotics is not is data. Like data is missing in all form. We can use simulation to scale it. We can use human videos, or we can use these glove-like systems to scale it, etc. But the main thing is to bridge the gap between sim to real, video and real. And for that, we need a full stack picture. We need to adapt sim to real. We need to adapt across videos. We need to look at optimization, look at the full stack in the whole scenario. And scale with low-cost robots, work with low-cost hardware. All the robots I showed in the talk, none of them cost more than $4,000. Whether it's a hand, whether it's an arm, whether it's a legged robot, everything under $4,000. And that's how we can truly democratize the space. So with that, thank you.
I have a quick question from the audience. Anyone can come here and ask.
So for the measure, the split and aggregate, how is it compared with soft AC? It's a maximum entropy.
Yeah, don't even compare. They don't even them. I mean, there are. I've been doing reinforcement learning for the last 15 years. There are like 100 plus algorithms out there, right? But the only one used out there is PPO, right? PPO is the only one used out there. It just works really well. So all these SAC methods in benchmarks, everything look good, but in practice, nothing is used because PPO just performance-wise works very well, right? In these tasks, nothing works. Everything is zero. Like you can add SAC, you can add whatever, and I can go to detail as to how it works. But the underlying thing is PPO works. It's a good algorithm. It's just slightly broken, and you have to fix it as you go across. That's the main lesson. All the other methods, they are not at all close. Like nobody uses SSC for ChatGPT or O3 or O1. Why do you think they should use? Like it's all policy. It just doesn't perform as well.
Thank you.
Hi, thank you for the talk. Also, I have a question about SAPG. Actually, two. The first one is if you do off policy, like if you're effectively off policy, right, with the diverse policies, but then don't you hit constantly the clipping limit and don't actually train on it?
Yeah, this is a very, very good question. So here, these are not truly off policy. But one thing I skipped is that across these iterations, you reinitialize the children from the parent or the leader policy. So they are far from, they're actually not too far from the leader policy. They're just more diverse. So it's not like it's a completely different data. So it's not yet off policy, but the idea is very much like off policy into on policy.
You kind of just broaden slightly.
Yeah. And I would say one thing though, my goal here is not to say that any of these methods are data efficient. They are super data inefficient. But the argument is you don't care in simulation. Data is cheap, data is free. What you care about is as I add more data, more compute, can it work? Getting the behavior is more important than getting it cheaply.
Follow-up question. Could you solve the same problem with, because I understand, my understanding from your talk was that the problem is that maybe the Gaussian parameterization is very inefficient in sampling large amounts of data. But if you use a tokenized...
So I don't think it's about Gaussian. It's not about Gaussian parameterization. It's about network. No matter how you parameterize it, the network you are learning is getting biased towards positive over time. Or some examples, yeah, it's an open problem, by the way. It's like if in life you only see one kind of positives, how do you know? Like let's say you are doing AI, and in AI you get a lot of success, a lot of accolades from around the world. How do you know if you did bio, you would not get praise also? It's a very hard problem, right? So it's the problem of the network. The more, because data collection is done by the same model that is being trained with the data being collected. So there has to be a bias over time. The way we deal with this in evolution or humanity is that all of us have different brain. So we will not do the same thing. Somebody will do biology, somebody will be a doctor, somebody will be, so at least we are covered on that front. If everybody did AI, I would be scared. Like we all should. So the same idea here, by dividing explicit separation, you ensure that the diversity has to be there by design. Parameterization won't handle it by any means. That's what I feel.
Thank you very much.
Hi, Deepak. Thank you very much. It was very cool talk, a lot of progress. I was wondering if you can tell us a bit of your perspective of the future. I mean, like these things you're presenting, do you think it's just a matter of scaling them, or are there still something, like some foundational things that are missing?
Yeah.
So, yeah, how far are we from these kind of general policies that you described at the beginning of the talk?
It's a very good question. I would say in terms of progress, I think we are almost there if you specialize the task. Like I said, many tasks, many environments. But if you say one task, many environments, and you pick any task, I think we have all the recipes to solve that problem. And which is where we'll see a lot of progress in the next few years. If you say every task, every scenario, like human-like setup, I actually do not know. I don't even know what we are missing because we are so far off from that. But if you specialize the task, there are many tools here. Like I can use simulation scaling, you can combine with some task. Task specification will make a lot of progress. And I think that will move to more and more, like locomotion, I was saying. Locomotion is kind of done. Like we can create these papers, some modification, but it works so well. Even off-the-shelf robots now come with such a good policy that it seems pointless to really improve that too much. Same with drones that happen. Now drones have become so well out of the box that there is no scope for research really over there. But for manipulation, it's not one task. Manipulation is billions of tasks. And that's where the bug stops. We only have techniques to solve task-specific models. We don't have a technique right now to solve multitask scenario. So I don't have a good answer. What is missing inside? It's an unknown problem. I think one idea could be to combine all these together. We know it has to have diversity, some learning from human to put them together, but I think there's missing a lot of things.
Thanks for the talk. I have a question about the literature. So for the algebra-based algebra observation condition policy, I think there's not much literature for simulation RL, and somehow many people are just doing algebra observation plus BC.
Yeah.
Do you know why people are not doing like RGB observation based RL? Like, is it because of like simulation bottleneck, or is it because of some architecture bottleneck, which like Gaussian pulse may be a problem?
Because I think that it's because the simulation land has been more end-to-end, end-to-end as in nothing in between, like really trained from input to output. And if you're doing that, and you train from scratch, you train on 100 billion samples. You cannot train big models at that scale. Like none of these robotic results I showed, none of them were big models. They were all like 10 million parameter models, like very, very small models. So the issue is I'm training from scratch in simulation. If I train from RGB, we know that simulation RGB doesn't match real RGB. It's very far off. So people just did not use that. They used depth, and it worked for many scenarios, right? Now the challenge is you could say, okay, I could use pre-trained backbone from real world, and that kind of works. But then you have to have more money, as in because it will take longer to train, more GPUs, etc. So and then again because 100 billion samples of training with simulation with a bigger model is just very expensive. I think that's pretty much the only reason. There is no fundamental flaw in the argument. And now, but today, the simulations are getting very, very expressive, very, very nice. Actually, there's an example of this. Like all these Gemini models, the Gemini models compared to ChatGPT models, they have really good understanding of 3D. Like they can draw 3D bounding boxes and all that, right? Now, you would say this data doesn't exist out there. How are they even training that? It should not have that property, and nobody else has it. They have that properties because Google has big teams that create sim data with these annotations, and they incorporate those annotations into these models. So they are already doing simulation RGB. Just because they are training a lot of real data, it just transfers really, really well. Now, the amount of money you are not putting that money in robotics right now is because it doesn't make sense. You have other problems. Like I can do RGB, but if my robot cannot pick up an object reliably or throw it reliably, it's all waste. So we are at least tracking the field by 5-10 years. Like we are still solving SGD problem. My whole talk was about SGD of robotics is not there. SGD, Adam SGD, like the optimization of robotics is not there. We used to talk about this in Vision in 2014. No, you will not find a paper or a talk about SGD of Vision today. It's boring. Nobody will show up. So that's it's just a matter of time.